Okay, good afternoon, everyone. Well, in the last lecture, we were solving this problem, and we have solved first three parts or first two parts. We have solved part A, and part B. Okay, we have solved first two parts, and now the last two questions. The question C is asking to calculate the total instantaneous and time average power carried by the wave. So the power density is uniform throughout space and does not depend on location, uh, except for phase, and therefore both the total instantaneous and time average power are infinite. Uh, this is true. This is true for any plane wave. This was the answer to the question C, and if we switch to D, okay, we read that suppose a receiving dish antenna is 1 meter in diameter. How much power is received by receiving antenna if the surface of a dish is perpendicular to the direction of propagation of the wave? So, question D. In order to calculate the power received by the antenna, we need to multiply power density by the surface of the antenna. So we have a dish with a diameter of 1 meter, and correspondingly the surface will be PD squared over 4, PD squared over 4, and is equal to P multiplied by 1 over 4, and okay, approximately P divided by 4, 0.7854, 0.7854 meter squared. Okay, and the power density was calculated in previous sections. Here we calculated the instantaneous power density, which was the Poynting vector, and it is equal to Z multiplied E0 squared over eta 0 multiplied by cosine squared omega t minus kz. Okay, let me write it one more time. Power density of Z and T as we computed is equal to Z so E0 squared over eta 0 multiplied cosine squared omega t minus kz. This was the power density. The unit of measurement is watt per meter squared. Okay, and in order to find power, first we find instantaneous power received by antenna, and after we find time averaged power received by antenna. Now, in order to find instantaneous power received by antenna, we take instantaneous power density and multiply it by the surface of antenna. So, instantaneous power is equal to modulus of power density. Just in order to have a positive sign, I'm taking the modulus of power density multiplied by S. So E0 over eta 0 multiplied by P d squared over 4 multiplied by cosine omega t minus kz. And so E0 was given as 1000. Okay, 1000. So E0 squared. I forgot here to put squared. 1000 squared over eta 0 is the impedance of a free space. No, wave impedance in a free space, and is equal. It was a constant 377 multiplied. So the surface of the antenna is we have already calculated and is equal to 0.7854 multiplied by cosine here cosine squared, don't forget cosine squared omega t minus kz. And okay, let's compute the numeric values. 1000 multiplied by 1000 multiplied by 0.7854 and divided by 377. 2083 2083.29 multiplied by cosine squared. Omega t is in our case omega is frequency is 300 megahertz, so 300 megahertz multiplied by 2p will be 6p multiplied 10 to the 8 t minus kz. Well, k okay minus okay, we have found the instantaneous power received by the antenna. Now we may calculate the time averaged power received by antennas. Okay, now the time averaged power received by antenna is P average is equal to the time averaged power density multiplied by again by S. Okay, time averaged power density is this 1326.3 1300 1326.3 multiplied, and the surface area of our antenna is 0.7854 0.7854, and the average power will be equal to 1326.3 multiplied 0.7854 1041.7 1041.7 watts. This is the time average power received by antenna, and this is here also the unit of measurement is watt, and this is the instantaneous power received by antenna. And this is the time average power. Okay. Well, let's look to the next example. Okay. Okay, the problem is saying a cylindrical conductor of radius A is made of a material with conductivity sigma and carries a direct current I. Calculate the power loss for a segment of a conductor L long. The conductor is shown in figure. Okay. How do we proceed here? Well, this problem can be solved most easily using the method where the resistance of the conductor may be calculated directly, followed by calculation of losses using Joule's law. But, however, we will use pointing theorem using the receiver case to calculate the losses in the process, gain some insight to the loss process. Okay, we use equation of pointing theorem Well, equation of a receiver case of a pointing theorem was if you remember, we have already discussed this in the last lecture. The integral over the closed surface S of E cross H ds is equal to minus d dt integral of V mu h squared over 2 plus epsilon e squared over 2 dv minus the integral over the volume V minus sigma multiplied the integral over the volume V e squared dv. Well, in our case, the time derivatives in this derivatives in this equation are all zero, or we may say that this term goes zero, and the equation becomes the integral over the closed surface S of E cross H ds will be equal to minus sigma integral over the volume V e squared dv. Now we can calculate the right hand side, which is exactly Joule's law. However, we said that the right hand side is exactly the Joule's law. However, instead of calculating the right hand side, we work with left hand side, or we evaluate the left hand side. Okay, let me copy this to a new page and continue there. So the current density in the conductor, in our case, in the conductor, is uniform and equal to J J equal to unit vector Z and I over S, where the S is P A squared, where A was given as a radius. So inside the conductor, J is equal to sigma E, and this is directed in Z direction. Therefore, the electric field intensity is also directed to Z, in the Z direction, and is equal to J over sigma, or J is in our case I over P A squared, and is equal to I over sigma P A squared, and is volt per meter. And so, and what about the magnetic field intensity? Magnetic field intensity H at the surface of the conductor may be calculated from Ampere's law, which we already know. So okay, taking a surface around the conductor at, so taking a surface around conductor at r equal to the radius of cylinder, or r equal to a, we get integral over the closed contour C of H dl is equal to I and from here we may write that H is equal to the direction of H in the direction of the unit vector phi I over 2 PA. And now, the power density at the surface of the conductor, which is P, which is E cross H. The power density at the surface of conductor is Z. E is equal to Z I over sigma PA squared. I over sigma PA squared cross the unit vector phi I over 2PA. So 2PA. Okay, what was the cross product of Z and phi? Okay, cross product of Z and phi. In cylindrical coordinates, it was equal to minus the unit vector of R. And so what we get is minus R I squared over 2 sigma P squared A cube. Over 2 sigma P squared A to the third power. And the unit of measurement is watt per meter squared. Well, this is the power density entering the conductor through its outer surface. So you may note that for a given current, the dissipated power density is inversely proportional to the conductivity. Here you may see. Conductivity is in the denominator. And the most interesting aspect of this calculation is that this power is directed into the conductor, which means that it must be dissipated in the conductor. The total power is the integral of this power density over the entire surface of conductor. In the case of the cylinder of length L, the surface is made of a cylindrical surface and the two bases. Thus, we evaluate the total power P from the equation that we have already used in previous problems. So Again, all the time derivatives are zero, which we have already discussed, and the total power is equal to the integral over the surface S of P ds. As we have already said that cylindrical surface consists of three surfaces, which are first is the uh, first is the cylindrical surface, the integral over the cylindrical surface of P ds plus integral over the surface of lower base of cylinder plus the integral of over the surface of upper base of the cylinder PDS. Okay, and the unit of measurement is here is watt. So okay, let me here put the indices in the first integral. I denote as ds of C, or the surface of the area of cylindrical surface, ds of L, area of lower base, ds of U, the area of upper base. And now the dsc, or the surface vector of cylindrical surface, in our case is equal to r a dphi dz dphi dz, and ds lower base is minus z ds, and upper base and the ds of upper base is plus z ds. It means that, okay, this last two integrals simplify each other, and remains only the integral over the cylindrical surface. So let's compute this integral. Okay, power will be equal to the integral of cylindrical surface of power density P multiplied ds C, n is equal to minus cylindrical surface of P was equal to Ri squared, Ri squared to sigma P squared A cube multiplied, and ds of cylindrical surface was R multiplied A, R multiplied A of df or dphi dz, dz. So what we get? R multiplied by R gives 1. A and A simplifies. A and here 1 of A simplifies, remains only A squared. And now, okay, integral. Okay, let me write a double integral of I squared over 2 sigma P squared A squared dphi dz. Okay, and the limits of the first integral or limits of phi, in our case phi equals 0, phi equal up to 2p, and limits of z will be equal to 0 and z is up to capital L, because capital L is given as the length of the cylinder we are dealing with. I squared over 2 sigma P squared A squared multiplied by 2p multiplied by L. Okay, 2 and 2 simplifies. Sorry, here p squared. P and 1 of p simplifies, and what we get is the power dissipated is I squared L over sigma P A squared. And okay, here we forgot the minus.